Hello. Hi. Good evening, everyone. Yeah. Okay. So, yeah, the question was what is the syllabus, right? Quiz one syllabus is same as one to four. Week one to four, and quiz two is five to eight, right? So how many of you watched the lectures for week five? Aditya, who else? Okay. Okay. Fine. So yeah, one lecture. Okay. Anyone else who has watched lectures for week five? Or if you are planning to watch lectures, what is it? One lecture. So what should, yeah, okay, what are you expecting today from the session? Shall I go through everything, like whatever is there? No? Or two lectures, one lecture? Are you planning to watch lectures in 1 or 2 days or something like that? Okay. Okay.
Actually, sir,
Hmm.
good evening, sir.
Yeah, yeah, Nisha, yeah.
Okay, so the thing is, whenever we attend this summary session and attend the lectures afterwards, they are better understandable. That's why.
Okay, if we tell you the summary and then you'll watch lectures, that will be better, you're saying?
Yes, sir. I tried this for 2 weeks. It was better that way.
Okay, fine. Then I'll start with the summary then. It's okay. So why I
Okay.
asked you this question is, if you guys wanted to watch the lectures first and then come back for a session, uh, then we can like arrange the session after 2 days or something. If not, then I'll start. Uh, along the way, you will try to understand it. So see, because I wanted you guys to participate into the, whatever the session is there, so that way I'll understand that okay, you are understanding it better or not, right? So that was my intention for the session. Okay, then let's start the session then. Whatever I can explain, maybe I'll try to explain it, then you can watch lectures, right? Okay. uh, okay, so is my screen visible?
Yes,
Yes,
sir.
sir.
Right.
Yes, sir.
Okay, so until now, until week 4, what you have
Sir, you're not audible to me.
now?
Now you're audible.
Yeah. Okay. What the question is? What is unsupervised learning? Am I audible?
Yes, sir.
Yeah. Tell me then. What is unsupervised learning? Means, what I'm asking is, what is the difference between, let's say, supervised and unsupervised learning? That is my question.
In supervised, we have the labels.
Yeah.
The
Yeah.
y is given.
Yeah. And labels are given to us, and in unsupervised learning, in a data, right? Whatever input data we are having, or training data, we say generally, we don't have labels in the training data, right? Or during the training data. In supervised learning, we have labels along with your input features, right? So let us say, okay, the setup is, general setup is like this: x1 to xn, and where each xi belongs to what? Rd. What does that mean?
D-dimensional space.
Right. So how many features will be there in each of x1?
D features.
D.
D features, right? And okay, by looking at this data, what you are able to relate in terms of a table. If I wanted to formulate the table with respect to this input x1 x2 to xn, what do you or what you can say about it, like about the data?
Capital X is D cross N matrix.
Right, so this will be looking like this, right? So suppose I have some features, let's say f1 f2 up to fd, right? D features, and I'll have some values here, right? And that vector is called, let's say, x1, right? Is x2. X2 will have some values and like that, right? Up to xn. Is it like that? Right?
Yeah.
Yeah,
Yes,
we
So
usually take the transpose.
right, so basic structure, it will be looking like this, right? And this is like x1 transpose. Suppose if I wanted to represent it into the matrix form, this each of this row will represent as x1 transpose, right? Correct, because x1 will be like this, the values for f1 f2 up to fd, right? Is that fine? Understanding this into your mind is important so that we can proceed further. I hope this is clear to everyone, right?
Yes, sir.
What do you mean by features,
Yes, sir.
sir?
Features means, let's say you have I'll take one example. Have you seen that like very popular example, which is house price prediction data, right?
Yes.
Correct.
Yes.
So what are the features there? uh, let's say it have area, right?
Location,
Area,
location.
maybe a distance, or distance from school or something, distance from metro station, some other number of bedrooms, right? These are the features, correct? And it will have some values, right? So area might be like 250 meters square, or square feet, sorry. And let's say 1 kilometer, right? And the number of bedrooms will be 3. So this will be the feature values, right? Correct, na?
Yes, yes.
Now you understand. So this vector will look like x1 will look like 250, 1 and 3. Fine. And similarly x2 will have some other values for those features. So that is the meaning of features. Is that fine? And in the matrix format, how will you look at it? Like x1 will be like this, x2 will be like this. So if I have a d cross n matrix, how it will look like? So here you have feature values, right? And here you have x1 x2 like that, right? So basically this will be x1 transpose, correct? This x2 transpose and so on to xn transpose. Fine. If I wanted to see that x vector, feature vector, or sorry, x matrix, feature matrix, right? I, this is fine. All of this makes sense.
Yes.
Yes, sir.
Uh, Sorry, I think there is a mistake, right? Okay, if it is a d cross n matrix, then it will not be like this, no? You have d rows and n columns, right?
so the exercise will be in columns.
Yeah, x1 x2 and up to xn, right? So if it is a d cross n matrix, that's okay. It's okay. You don't have to worry about all of this thing. Just try to understand that what does that mean. So when I say each xi will have d dimensions, what does that mean? This will be the feature values, right? Let's say this is area, this is distance, and this is, let's say, number of bedrooms. Fine. This is okay.
Yes, sir, clear.
And
Yes.
it will have some labels, the corresponding labels, which are
What have you written there, sir? Features slash what? On top.
attributes. It is called features or attributes, right? Okay, maybe I'll write it like here. Attributes, fine. Okay, and you have corresponding labels to each of these examples, right? And what do you say about those yi's? What are the dimensions? If I wanted
R.
to find, right? It's a real value only, right? Because if you see that, it will be so if you have the price here, right? and price will be your y, right? So y1 will be one value, right? Some say 5
Will
lakh.
it be a scalar, sir?
Yeah, it will be scalar, right? So that's correct, right? That's okay. Wha- what are whatever the values will be there, depending on that will define the problems, right? And you have three types here, if you know properly. So there will be one called as the binary classification. What is that binary classification? You have two classes, right? Maybe +1 -1, or positive or negative class, or 0 1, whatever is fine, right? So let's say it's a positive class and negative class, it is called as a binary classification. So what is the value of y here? Each y will take the value in this case
Plus
either
1.
+1 or -1, right? Or 0 or 1. How you have defined the classes depending on that, right? There is one other term which is called multi-class classification. It can start from 0 or it can start from 1 also, like it doesn't matter. uh, it will be multi-class classification. So what values y will take in this case?
0 to k.
Yeah, any value between or any value between 0 and 0 to k, right? Okay. And our regression problem, what will be the value y will take? Any real number, right? Correct. And that's your regression problem. Is that fine?
Yes, sir.
In this case, if I define this house price prediction, it will be all the values, right? The price values will be your real values, and hence that will be your regression problem. Okay, what is the goal in this case, in our regression problems or in supervised learning problems? Generally, the goal is to predict something, right? Predict the output, basically, right, based on the training data. Is that fine? It's like it's a vague definition, but yeah, it's kind of a broader definition, I'll say. That is your a goal here, right? To predict something or predict. In this case, what will you predict? Given some test data, right? You given some test data, you wanted to predict the price of the house, right? So you'll have some features given to you, and based on that, you'll have to predict about the price. That is our goal in supervised learning, and in this term, in this case, regression problem. Is that okay?
Yes, sir.
Right. So now we'll think about regression, whatever I said now. In that case, what is your input data?
What do you mean by regression, sir?
Regression. Okay. So, okay. So, have you completed your MLF part? I say, have you gone through the MLF, or you're just doing MLF by side by side?
Side by side, sir.
Okay. Okay. So regression is generally, means like, I don't know what is the exact meaning of regression in English terms, but it is kind of a when we say linear regression, it will be a fitting a line, or in general, what is it? Uh, uh, if I wanted to say that for only regression, right? So that means your whatever the data points are given to you, you try to fit all the data points. That is the basic definition. Linear regression is kind of a I'm trying to fit a line through the given data points,
Okay.
right? So I don't know where that word comes from. Maybe some Latin or something, I don't know. But yeah, you can actually search for it. But that is a basic understanding of regression. Okay. Okay, so let us say, and what is the setup now? You have input data which will be looking like this: x1 to say xn, and each xi will be in d dimensions, and you have some labels, or maybe I'll say output, right? In this case, it will be y1 corresponding to each x1 xi, right? And you will have some x y1 to yn, and each yy will be in R, right? Okay. What is your goal? You said you wanted to find or you wanted to predict the label given some test data, right? Or test input. Uh, that is your goal. So it's kind of you wanted to learn a function, right? Basically, what is the definition of function? So you generally have some input, right? And you wanted to throw some output, right? That is kind of you'll have a domain and you'll have range kind of thing. If you remember from your maths, right? Is that correct?
Yes, sir.
So here, what does that mean? I will input everything, this thing, right? The training data, in which okay, training data actually constitutes everything here. This input and the labels. I'll I'll learn some function and I'll give some output. So what are the dimensions of your input? D dimensions, right? And what do you want your function to throw? One real number only, right? That is my goal,
Yeah.
right? And that is called a function h, which learns from the given input data and tries to, predict the uh, next data point. Okay. So again, how will you say that? Okay, how many? So let us try to understand through maybe 2D problem. Suppose you have one feature x and you have one label for that feature as y, right? And if I try to plot all of these data points, suppose these are my data points, okay, right? Suppose these are the data points, okay. How will you say that, and how many functions can I use here to see that, okay, whether these data points will be, you know so okay, how many functions, first of all, okay, how many functions you can see here, which will try to fit in to these data points? Okay, what are the functions? Basically, let us say h of x will be, I can say x, h of x will be, let's say x square, x will be some x cube, like that, right? These are the functions, right? Different functions. Maybe x square, x cube, something else. Let's say x plus c. Uh, what else you can have? Any polynomial function you will try to fit, right? So, which will be a better function here that can, what do you say, like that can be uh, used here to fit these data points? And how will you say that this will be a good function?
I think x cube is a
X,
good.
X square.
Okay, maybe x square, maybe x cube,
X
right?
square
Definitely.
because it's
Right.
like a parabola.
Parabolic. Okay, but that is okay. That is like you know that this is a good thing, right? Because you are able to visualize it. But how the machine will learn that that will be a correct thing? And how will you say that what metrics you should use that this will be a good function among all these functions?
You have to
The
calculate
square
the
error
error.
should be.
Square error.
Right? So you'll try to find out the squared error, uh, right? And what does that mean? What is squared error? How will you define the squared error?
Variance.
Huh?
H of x minus yi whole square.
Okay. And what will be h of x? It's a predicted label, right? Is that correct? Predicted label for y, right? And y is your actual label. Is that correct? Will that be fine? Yes, no, something.
Yes, sir. That will be
Yes,
the
sir.
square error, and sum over all the errors.
Sum of? Yeah.
Sum of, yeah.
So, and the error between these two will be your h of x minus y will be your error, right? And if I use like all the data points, so h of xi and yi, right? So basically your error will be this one. Is that correct? Summation of, so this summation, when I'll take summation, that will be your uh, total error, right? But then will this be a correct metric, or shall I do something else? Why shall I square it or not square it? And why should I square it? Can you just justify for that?
Yeah, it can be either in the positive side or negative side. So square it.
So what actually gives the square error? Why we choose that square error? Uh, okay, that is again the important topic to discussion, right? Generally, people use this error, but there are different. I can use the absolute error as well, right? Why I can't use the absolute error? But okay, so let us say we use this h of xi minus yi as the error and as the squared error. So this is called as the sum of squared error, right? Sum of squared error. Let us say we have used this sum of squared error as your metric. How will you say that this will be a good metric then, or how to utilize this one?
To minimize
Sir,
it.
So
uh,
yeah,
sir, just one question. Sorry to interrupt,
yeah, yeah,
but sir, I have some doubt in practice assignment. So should I ask it in the end of the session?
yeah. That's okay. Yeah. We'll do that. We'll see from which week? 4, huh?
Yes, sir. Week 4.
Okay, okay. We'll take it. Hmm?
Okay, sir.
Yeah,
Thank you, sir.
yeah. So, what is the importance of this error now? I have defined some error, and h of xi will be anything, right? Any polynomial function we can use. And how will you say that which function should I use this based on this, right? Based on so whichever function gives me a least error, right? And that will be my goodness of measure, right? So, or that will be a good function for me. Is that correct? So because see what functions will be there, I can have, let's say, this function. This is what function? So is this h of x is equals to basically it is equal to, let's say, x, right? Is that or some slope, let's say cx. Maybe I can have another function which is suppose like this, which is called h of x equal to, suppose this is some cx square, I don't know. Then I can have some other function which can be looking like this, right? So some function, if you are able to have some h of x, some difficult combination, right? Let's say cx plus or c1x plus c2x square plus c3x cube plus c4x raised to 4 or something like that, right? I can have any of these functions, and how will I say that which function I should use? Whichever function gives me a minimum error, that will be a good function for me, right? Now you are able to say, right, among these three, which will you feel that is a good function?
The
The red
quadratic
one.
one,
The quadratic one. Why not this one, the red I have drawn here?
because it is overfitting it.
Okay, what is overfitting?
We are just memorizing the data,
Okay,
not learning it.
okay. Okay, overfitting is yeah, okay. So there are like multiple ways to define it. Okay, but let's try to understand that it is giving me the zero error during training, right? Whatever we are doing here is the training part, right? We are not, when I say the test part, whenever my new data point will come, right? And based on that, what my model gives me the output, that will be my test or that will be my test data or test output, right? Currently whatever we are doing is a training. What we are trying to do here is we will try to find out which is a good function, right? And for that, what we have said is error, the squared error will be a good metric to have. And what we try to achieve through this is minimum error, right? That is the whichever function gives me a minimum error, that will be my that is the function I'm going to choose. Is that correct? So ideally, what should you wanted to have now? In ideal case scenario, this error should be what, like as high as possible or as low as possible?
as low as possible.
Lowest possible.
As low as possible, right? And if I say if it is as low as possible, what will be the lowest value by looking at this function? Will you say?
0.
Right, that means it is going to perfectly fit all the data points, right? So h of xi, the value of h of xi will be exactly equal to yi, right? I will not have lesser than 0, right? Because of that squared term, this error will never be less than 0. Is that correct? So the minimum value I can have of this error is each of this data point, or whatever function I am actually defining, it will fit exactly to my uh, the label, right? And that will give me the 0 error. So the minimum error, ideally minimum error will be 0, but the problem will with that error is what then, or with that function is that it might not perform well on the test data point, right?
Test data.
Right, so that is the problem. And again, finding out that many, so if I say that h of x equal to c1x plus c2x plus x square plus c3x cube, how many parameters will need to learn here? So they are more than, like, it is very complex to again to learn all these parameters, right? Instead of learning only one or two parameters or something like that, right? So that's why we don't actually we know that this might not be good for our testing purpose, right? That's why we choose a simplest structure, which is a linear structure, and hence we use h of xi as what? Generally, we don't use a quadratic one also. We just generally use h of xi as a linear structure, right? It will be a linear. So what we'll do now? We'll search only in terms of linear structure. Is that fine? And
Hello,
we'll,
sir.
yeah,
Sorry to disturb you, sir. Which topic you are discussing today?
linear regression, the fifth week 5.
Week 5. Okay. Okay.
Okay. So okay, so if I say that I'm going just only to use the linear structure to fit the data points. So in that case, let's say you have this x and y, right? Suppose you have some data points like this. Now with this case also, will my error, do I need to go for error, or I can just say that okay, this is the line. How will I learn here? Or shall I use the error matrix here? Okay. Any questions or any answers to this part? Do you understand the question?
Can you repeat, sir?
Yeah.
Sorry.
Okay. How many? So when I say that there are different functions I said previously, right? I said like there will be a quadratic function, there will be cubic functions, there will be any polynomial functions which we can use, right? Or sinusoidal functions, cosine, whatever things we can use, maybe exponential functions. If you can, we have this set of functions, right? Why we are not going to use all of them, all of these functions is, one thing is they are very difficult structures, one more thing to learn. Another thing is what I said is they might lead to overfit the data, the training data. What does that mean is, during training they will give you the minimum error, but during the test point, right, they will not perform better. That means they will not be able to give the good output, right? So or prediction. So that's why we said that we are going to use linear functions only. So if I wanted to use linear functions, shall I use this error functions again? What does that mean now? What we are actually searching here, if I try to minimize this error, right? So our goal is to minimize the error, right? So in this case, what should I get it? So what does it mean? Okay, there are
You
different.
can use an error function in order to
Yeah, what
check
this
for
will
the.
give? Yeah, like what we are checking here?
I mean, we have to minimize the error
Huh?
so that the data fits into the.
Yeah. So here, if I choose this linear structures, what does that mean? If I'll have so many lines right here, I will
Yes.
choose one of the line out of it by reducing this error, right?
Hmm.
Is that correct?
Yes.
And that will be, let's say this line is there. Not sure about this, but let us say this is the line which minimizes the error, right? By looking at this, maybe I can say that this might be a good line. What does that mean by this is a good line is, what is the uh, what what is the equation of this line now?
So it's a line linear function.
So this can be like wx.
Hmm.
So
Plus
w is some,
some constant
yeah, okay, so
B.
plus some
Hmm.
constant.
because it's not passing through origin.
Correct. So,
Hmm.
right. So let us say it is passing through the origin now. Will this be without? Okay, I'm not. Maybe okay. This is a bias term. We can use actually bias term, but it's okay. So now that will be my line, right? Which gives me the error. And how to find out the error in this case? The errors will be like perpendicular, right? To this data point, right? Is that correct? So
Yeah,
for
drawing perpendiculars.
yeah,
Hmm.
so let us say for this data point, whatever my actual what is the predicted value here? This will be my predicted value, right?
Yes.
And that will be my actual value, and that is the
Hmm.
error which we'll try to minimize, right? If I wanted to minimize that error, might be this might be a good line, right? It's like among the so many lines. So if I change the parameters here w and b, I'll get different lines. Is that correct? So does
Hmm.
that mean like I'm just saying that if I change the slope and the intercept here, I'll get different line, but I am choosing that line which will gives me a less error, and it will have, let's say, this slope, right? W star and B star, right? This is my optimum line I am choosing, right? But this is I am able to visualize in 2D format. Is that correct? Like I have
Yeah.
only one feature and I have one label for that. Like let's say I have only X feature and Y, right? But in general, we are dealing with the data in which X will have how many dimensions? D dimensions, right? So how many parameters do I need there? If I wanted to like fit a linear structure there, how many parameters will be there? And okay, how many parameters? That's a different question. Let us say, what should I do? I should be dealing with some matrix, right? So,
Hmm.
so my x1, x2 will be like this, na? Let's say x1, x2, and
XD.
xn,
XM.
right? Because this is d cross n. So the features will be along the rows, and that is my x matrix. And if I initially what happened is here I have one x, right? Correct? Let's say it's d cross 1. Is that
One.
okay? 1, right? D cross 1.
Yeah.
D features, suppose, and one column or something like that. And how how many parameters I need here then to define this? Or how this W vector, will that be a vector? Will that be a matrix? What can I say about it?
Mm, it
Or
will
is
be
it
a vector, I think.
right? So actually, I'm trying
Hmm.
to.
Vector.
So when I say h of xi, it will be like this, right? So okay, will see try to see it in terms of uh, matrix. So let's say here x1, x2, here it is xn, and I will have one vector, right? Suppose this is my d cross n matrix, and I will have one
N
vector.
cross 1.
I'll have a vector w. What does w will give me? Like It will be like w1x1 plus w2x2 like that, right?
Hmm.
That is my and it will be basically d cross 1. Why d cross 1? Because you see, if my
We're
x1
taking W
vector,
transpose.
yeah, if I am having x1 vector, which is in d cross 1 dimensions, I should have that many weights, right, to multiply each of that value. Is that correct?
Yeah.
And similar weights I wanted everywhere. Is that correct? So I wanted those weights such that all of this structure will be like will give me the minimum error. Fine. So in matrix format, how will I multiply them? This is basically x1. When I say w1 x1 in matrix format, how should I? This is a dot product between w and x, right? W1 x1.
Yes.
So in matrix format, how will it will be written as? Can I write it like this? X1 transpose w1.
Hmm.
Why I'm writing this x1 transpose w1? Because each x1 is having, so each xi, so xi is in d cross 1, w also is in d cross 1. Okay, sorry, here let's say w is also d cross 1. My output should be what? So it should throw me some real number, right?
Hmm.
That is my so when this will happen, I'll take a transpose and then I multiply, right? So x1 transpose w. So what is the transpose here? X1 transpose will have what dimensions? 1 cross d,
One transpose, yeah, 1 cross D.
and w will be d cross 1.
D cross 1, which
So my
is
multiplication would be one
a real
single
number.
real number, right? So basically, what we are trying to do here now. So we'll try to find out. Is it x transpose w, right, in matrix format? Are you able to see this now? Then only I'll be able to find out the answers, right? What will be the multiplication of this x transpose w? So it will be equal to x1 transpose will be like this, right? X n transpose, and what are the dimensions of this? Now n cross d, right? Multiplied with w, which is a
D
d cross
cross 1,
1, and what will be the output here now?
N cross 1.
Right, some n cross 1. So
N
n
is
cross
the
1.
number of data points, right, sir?
Yeah, so basically, because you'll need that h, so y n, right? Your actual, sorry, yi, right? Y is a vector. Is what is the dimension of this y vector?
N cross 1.
N cross 1. Is that
N
correct?
cross
N
1.
cross 1.
Correct, na? So your output here, this is basically what is it? H of x, right?
Hmm.
And then your output also should be of that dimension only, right? So this vector also should be n cross 1. That's when only you can be able to find out its right. So you will be able to subtract, right? You will able to find out the subtraction, and then you can square it. Is that correct? Now in
Uh,
matrix format,
So aren't H, X, and Y the same
we
same
wanted it
quantity?
to have, right? So what is so here in this case, what are the y's? So let us say in 2 dimensions, we'll try to understand this. uh, y will be here the black data. Okay, I'll draw some black you are able to see, right? The data points.
Yes, yes.
Okay, maybe I'll just draw it again. Suppose this this this, right? Let's say
Hmm.
these are the data points, and I'll draw some I'll rate data points. Okay, the vector y will constitute which or which values corresponding to the black data points or corresponding to the red data points? Vector y,
Red.
black, right? These are
Black.
the
Black.
actual values, right?
Acha.
Yes.
Right. So this actually this value, this value, this value. So actually, so all of these value, if I put it into a vector, these are the values which, because these are the actual data points, right? Corresponding
Yes.
to x. So this will constitute my vector y, and what
Mhm.
these red data points will denote here.
H, X.
Basically, can I say w transpose x, that vector,
Okay.
right? but they should be corresponding to each of this value, right? So the first value should be equal to that respect to that xi. Here xi is here, right? Are you able to now understand that what is the transition node? And what we are trying to do here is the difference between this, the prediction, the red data point and the black one should be as low as possible. Is that fine? So I wanted to, so if I just use xi and yi and summation of I equal to 1 to n, this is the algebraic form. What will be the matrix form here? W transpose xi minus
Xi minus
yi
square.
square, and again it will be a sum. Okay, sum of I equal to 1 to I equal to 1 to n, and I wanted to minimize here what now? So here it was like I wanted to minimize the function, right? I wanted to find the function, the linear function, right? Is that correct? We said that we are using the linear function. Here what we are trying to minimize, we have x, right? In our training data, we have this information with us. We have this information with us. Is that correct? We have the information of each xi and each yi. What does we do not have? We don't have the information about w.
W.
So we wanted to find the minimum value of this function such that or this w will be in d dimensions, right? So this function basically will be a function of w, right? Is that correct? Because here x and y are the constant. What is the variable here?
W.
W. So basically you try to understand that this is kind of a slope equation, suppose, right? Mx, general function, right? And I know the values of x and I know the values of y. I'm changing the slopes, right? And I'll try to find out that slope which gives me the minimum value of this, correct? So here I know x value, I know y value. I just wanted to change the slopes. I wanted to find out, because see, if I change the slope like this, so this will have some different slope, right? This will have some different slopes. But I have the input and the label already with me during training. I wanted to find out that slope which minimizes the this error function, right? That is a 2D way of thinking, and in matrix format it will be like w transpose xi minus yi whole square, and that will be a function of w, right? I hope this is clear. Okay, now what is the, can you just say, tell me that what is this? This will be a vector or this will be a matrix? W transpose xi.
This will be
It is a vector, right?
vector, yeah.
Vector for like one point, data point.
No, okay, yeah, okay.
Xi is a single.
Yeah, and
Yeah.
if okay, so let's say it's a value. So if I use it like along the summation thing, right? So yeah, this is correct. This is like related to one data point, w transpose xi minus yi. It will be one value, and if I do it for n, right, it will be a n cross one vector, right? Entire thing, this entire thing, correct? Or basically, it will look. Can I say that it will look like this? Square root of, let's say, w transpose xi minus yi, right? Summation, and I'm taking the square. So okay, I have to write it like this. Maybe I'll try to expand. I'll try to expand this term. How it will look like? W into, can I say, x1 minus y1 square plus wx2 minus y2 square plus
Yes.
wx3 minus y3 square, like that, right? Here I'm just doing it right like this. Okay, so if I just put it like this, all right, what does this gives me? it will give me the length of the vector.
Yes. The projection vector.
This will be a length of the vector, right? And if I square this term, then it will be a square of that vector, right? So can I say that this is a L2 norm? Will this be a L2 norm?
Too
Yes.
long. Uh,
L2 norm is basically the length, like finding a length of the vector.
okay. Mhm.
Are you able to visualize this part or like understand this part? If not, like
Yeah,
we can try it out. It's not a problem. We can try it out. But
yeah,
if
if
you
you
are
can
able to,
give a detail.
fine. So what is this wx1 value? So
WX1
basically,
is the
when we said,
vector.
right, this x into, if I had this matrix X, right, maybe X transpose matrix, and I had W, right, it gives me what? So X was in what? X was in R D cross N, right? That was the matrix. X transpose will be N
N
cross
cross
D.
D,
W will be
D cross 1.
D cross 1, right?
Mm.
So the output was X transpose W, whatever the output was there, it was some vector, right? Some vector with dimensions n cross 1.
N cross 1.
I have
N
some
cross
y1 sorry, y vector which was also having the dimensions as
N cross 1.
N cross 1.
n cross 1. And if I subtract these two quantities, so basically it was x transpose W minus y. So if you can just say that what is the quantity here, the first quantity will that be x1 transpose W? You can look at it, this part. What will be, so if you know the matrix multiplication, what will be the multiplication? X1 transpose W.
Into W. Mm.
What is the second point?
X2 transpose W.
W. But these are the scalars, right?
Sorry?
These are the scalars, the values,
Scalars, yes, yes,
correct?
yes.
Because x1 is d cross 1 and x1 transpose is
1 cross
1
D.
cross d, and 1 cross d into d cross 1 will be 1 cross 1, which is a scalar, right?
Yes.
So this vector basically represents what? X1 transpose W, x2 transpose W up to x
Xn transpose W.
x1 xn transpose W. Is that
W.
fine? And here let's say you have y1 y2 up to
Y N.
yn. So if I take a different, like a difference, what will be its difference? X1
X1
transpose
transpose W.
W minus
Y1.
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 Here x2 transpose W minus
Y2.
Y2.
y2, and like that here it will be
Xn
xn
transpose.
transpose W minus yn.
Yn.
Fine, but all of these will be scalars, right? Some scalars,
Yes.
because y1 also a real value and x1 transpose W also a real value. So these are all the constant, right? So basically this will be a vector of what dimensions? N cross 1. Done?
If you subtract N cross 1 with N cross 1, I
It
think
will be
result
same
will
thing,
be
right? Yeah,
same.
let's say 1 2 3 minus, let's say 0 1 2. What will be the final thing? 1 minus 0, 2
1
minus
1 1.
1, and 3 minus 2 1, right?
Mm.
And what is the length of this? Square root of 1 square plus 1 square plus
Yes,
1
1
square.
square.
That
Root
is
3.
what, let us say I have, let's say this is vector A. What I'll say, or what I'll say about vector A, it's a norm of A, right?
Mm.
That's fine. This is called L2 norm.
Yes.
Fine.
Well,
And if I take a square of it, how it will look like? The square root will go away and this will be like this. Fine.
mm.
Right now, that is our basic understanding of the vector norm, and it's like what is called as a length of square or something like that. So basically, what will be the length of this now? Length of this vector, the above vector which I am showing here, will that be like this? X1 transpose W minus Y1 square
Mm.
plus x2 transpose w minus
W
y2 square,
y2.
and like that
Yes.
plus xn transpose w minus yn
Yn.
square, and
Square.
if I take a square root, it will be my so what is the norm here? xt
X
x
X
transpose
transpose W
w
minus
minus
Y.
y
Norm
L2 now,
L2.
right? And right now, I'm not doing anything else.
Yes.
Like the same thing. But if I wanted to remove that square root, that will
So
be
you
then
can square the
just
square. Hmm.
that's fine. This is what exactly same as that of saying as I wanted to minimize the argument such that summation of I equals to 1 to n w transpose xi minus yi square, and I wanted to find w's which are in RD. Right? Basically, in vector format, I wanted to do what? I wanted to minimize this part, right? Minimize all of this, right? And how to write it now? So this will be a vector, right? X t transpose or minus y is a vector, and I am saying that it's a norm. So if you remember it, can I write it like this? X transpose w minus y transpose into x transpose w minus y.
Yeah, if we
Right? Because norm of
if we
A, I
norm
can, how will I write that norm or
A
norm of A
transpose
square? Yeah,
A transpose.
right. So that's what I'm basically writing it here, right?
Hmm.
Fine. And now the goal become what? Uh, minimize this part for W's, right?
Hmm.
And if you remember, like I don't know how many, if you guys have completed your MLF, this is a unconstrained optimization problem, right? Or if you don't like completed MLF also, what is unconstrained optimization? What is optimization basically? So let's say you have function y equal to x square. How will you find out it's like this is called as optimization function? Let's say I wanted to optimize it. What do? You take a derivative, right? And
Hmm.
set it to 0 to find the critical points,
Oh,
right? And that will be your solution, right? Whether it will be a minima or maxima, we'll check it in the next step. But you just generally what you do, take a derivative with respect to that value and set it to 0. So here it will be 2x equal to 0, which gives me x equal to 0, and that will be my critical point.
critical point.
And then I'll decide that whether it is a minima or maxima, right? And that is like taking second derivative. But basically this is your idea of understanding, right? So here in vector formats, or in the matrix format, or like whatever format you wanted to say, this is my definition. What is this function now? This function will be a function of x, function of y, or function of w.
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 This is a function of w, right? So if this is the function I wanted to minimize, what should I do now? Differentiate.
Differentiate with
Derivative.
respect to W.
Yeah,
Derivative.
but here the w vector will be like, it will be a vector, right? How many
Hmm.
uh, values, like how many variables it will contain? W1, W2, W3, W4, like that, right? Until
Hmm.
Yes.
d, right?
W.
WD.
D.
Mm.
So that means like it's not like single whatever we said, like y equal to x square, and if you have more than one dimensions, what you do generally?
Gradient.
Yeah, so basically gradient, or you take the partial derivatives, and generally we call that set of all the partial derivatives as a, like, you do it in a gradient format, right?
Yes.
Fine. So what will be the gradient here then? Del f of w.
So
And
why W is a gradient? Why you're saying
Vector.
like that?
so
W1,
suppose
W2.
suppose you have a function x square plus y square, right? Now what you do
Hmm.
to find out the next, so when you have y equal to x square, that problem, or f equal to x square, what do you do there? You just take the derivative with respect to x, right? And that will be
Hmm.
2x. But if you have more than one, then what you do generally? You find a
Partial
gradient,
Gradient we
derivative.
take gradient.
and gradient will be like,
Gradient. P.
this is the partial derivatives. So you'll just take the partial derivatives, right? 2x and 2y, and you'll
2y.
set it to 0, 0, right? Correct? Why we
But
need
here
gradient
also-
here? Because you don't have only W, the single value. We are not actually dealing with the one input, right? Which was X. It's like your input is in D dimensions. That means the values of W. So W will be a vector when I say that contains what? How does this W will look like? Will it be only single W, or okay, when I say this W, this is not
Vector.
W, right? It will be like W1, W2, W3, like that.
WD, WD.
In
Right?
all the direction we have
So
to see.
yeah, all these directions, right? W1, W. So when I multiplied that x1 transpose W, right? That will also like, it's not like single thing. What is the x1 transpose W? Basically, it will have all the values of x. I'll multiply it with each of this. Let's say it will be like x1 W1 plus, or how will I say, x11. Right? What is x11? The
First
first
element
value
of
in
first
the
row.
vector.
x1 into
First
W1
vector.
plus x12 W2 plus x13 W3, like that, right? So these W1, W2, W3 are the variables. So that means you have more than one dimensions, right? You have like, and
Got
then
it.
that's why you don't need that. You can't do that single derivative, like simple derivative. We'll have to do
We have to
for a
do gradient.
gradient, right? That's why we opted for gradient here, because this is W are having a lot of values. Clear?
Mhm.
Okay.
Okay.
Then, yeah, then in this case, what will be the solution now? You can actually easily find it out because whatever the general, right, how to find out the derivative, the same thing you can use. That will be your, the solution will be 2 into x6 transpose W minus 2xy.
2xy.
Okay. When
So
I
now
say
you get this.
Capital X.
you can actually okay, you can find it out. Okay, maybe if you wanted to see how it will be, can you just expand this term now? What will be the expansion? X transpose W transpose, what is the term? W transpose X, right?
W
W
transpose. Yeah.
transpose.
Minus
Mm.
Y transpose.
Minus, let's say, Y transpose
Y transpose.
into, let's say, X transpose W minus Y. What will be the multiplication? W transpose X,
W
X
transpose
transpose W
minus
minus
W
Y
transpose
minus Y
XY.
transpose.
No, I'm just multiplying with this like that.
Okay, okay.
Y transpose X transpose W
Y
minus,
transpose Y.
Y,
right?
Y transpose.
And what will be now if I want? We are actually differentiating with respect to W, right?
Hmm.
Mm.
So that
So Y,
means this quantity is
Y
constant.
transpose Y.
This quantity is constant. This constant quantity is also constant, right?
Yes.
This will be constant, and this will be constant, right?
Yes.
So what is like W transpose W basically is the W square, right?
W
Yes.
square. Wow.
So what will be its derivative? 2 times
2x
2W.
transpose.
x
Oh, sorry.
transpose
2x
W,
transpose.
fine, right? Minus here
XY.
xy, here
XY. Minus
xy,
XY. Yeah.
y,
XY.
right? And this will be 0, right?
Yeah.
So basically this will become like 2xy, something
2xy.
like that. And that is
Okay.
what I have written above. So okay,
Mhm.
I have done the like these calculations.
Yeah, yeah.
You can do like with, you can actually use the matrix and you can find it out. That is also fine, right? But you will get the same thing. Okay, what is the next step now you do in minimizing this problem? You will have to equate it
Equate
to
it to 0. 0.
0.
and if I equate it to 0, what I'll get now? I'll get so 2 will get cancelled, basically x6 transpose W equal to xy.
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 Okay, and
Oh,
now
yeah.
whatever this W, so here x is
W.
constant, xy is constant, so whatever x W here we are getting, that will be your minimum value, right? Or that ensures me a minimum value, and I'll say that it is my solution. So it's, let's say it is a W star,
Optimum.
right? Here, yeah, and this is x6 transpose will be a vector or a matrix?
Matrix. Matrix.
Matrix.
Matrix, right? What are the dimensions of it?
G cross T.
D cross T.
Okay, is that fine?
Yeah.
Now I wanted to find, basically my idea is to find W star, right?
Mm.
So what will be W star now? I cannot now it's a matrix, right? I cannot like generally like divided by a scale like we generally do. What you have to do? I'll have to
Inverse.
Invert.
take a inverse, right? So basically, I'm just multiplying the inverse on the both sides, right? And
Okay.
you know that, right? I'll have to inverse like here, right? And this quantity will become an identity matrix. So I'm not doing
Okay.
that step. I hope all of you know that. I'm just writing down the final solution, which will be x transpose inverse xy.
Exactly.
Right, so not x, small x. It will be a, yeah, because x is a matrix, right? X is not a vector. Y is a vector. So whatever small y I'm just representing, it is a vector. Capital is a
Matrix.
matrix. Is that fine?
Okay.
Yes.
But generally, what is like this inverse happens only when
It's
you are
invertible.
It is
invertible.
invertible.
That means the
Invertible.
determinant of
Matrix
that
is
matrix is not equal to 0,
Non-zero.
not
or
zero.
that is
Non
called
Not
as a
zero.
zero.
non-singular matrix. But if it is a singular matrix, then what will happen?
Pseudo-inverse.
Yeah, we have to go for a pseudo inverse. Basically, what does it mean is uh,
What is it?
if you are not able to find uh, the values, that means we are not like we don't get the inverse, but that doesn't mean I will not get a solution. There are two ways of getting a solution, right? If you remember it from system of linear equations, how to like how will you get the solutions? There are two solutions you can get. Is one is unique solution and another is, let's say, infinitesimal solutions, right? So unique solution you will get when your rank of the matrix maybe a full rank matrix with respect to the augmented one. Okay, I don't know. Some if you guys have uh, attended the MLF lectures of mine, I have explained there
Yes.
with respect to the matrix format. If you want, you can go and so currently I will not maybe go into that details, but that is the case, right? If you wanted to understand that with linear algebra perspective, you can watch that lecture. Is but if you understand here, right? You don't have if you don't have the proper inverse, you can get the help of pseudo inverse. Basically, this will required when you don't get so your matrix is singular, right? If it is not, this is a normal inverse. Fine.
Yes, sir.
So what is this plus
This is called
or transpose?
like this is not a transpose. This some right. So some this is called a pseudo inverse.
Okay.
How do you find pseudo-inverse?
Basically, inverse is
Okay, that is like you will have to watch some lectures from linear algebra how to find it.
yeah.
Yeah, it's okay. So you can watch like Gilbert-Stein lectures. You can just one video will be there. You maybe find it like fine. How to if you
Pseudo
are interested, you
inverse.
can go and watch it. Okay.
MLF, right?
What happened?
In MLF, right? This is pseudo inverse.
Another?
In the weak file lectures, I was saying pseudo inverse.
No, no. It is not like taught here. Like how to find out the pseudo
Okay.
inverse. You will
Okay.
have to watch like separately.
Okay.
It's a linear algebra thing, so you just have to.
Mm.
It is not difficult. You can just watch it. Like you will get it some like lot of places.
Okay.
Okay. Yeah. So you understand, right? This is what this is the optimum solution we get, right, for our problem, and this will ensure me what whatever line I'm trying to fit, right? That will give me a less error. Is that okay?
Yes, sir.
Right.
Yes.
Okay. So if you remember from the PCA, that solution whatever we are getting, right? Will that be the same? Like will that be a similar solution we were getting that time? Or will that be a different solution? Do you remember it?
There,
Yes, sir.
there it was covariance matrix.
Right. And was that covariance matrix looking like something this,
Yes.
right?
Yes, sir.
Like it was 1 by n x transpose, right? It was not basically
Right,
n,
sir.
but it was x transpose. And what we said is that time, if you remember, that will become computationally expensive
D is large.
when d is larger than the n, right? And that same problem will also happen here. Is that fine? Okay, and then we know that so I think there is a basic difference that we didn't have y term there, right? Because and why y
Yes.
was not there? It's basically it's the
Labels were not
not
there.
there, right? And that point we were saying that whatever the solution we are getting, that is a solution, that solution was some alpha times x, right? X alpha, something like that, x alpha star, and that means it is a linear combination of data points, we were saying, if you remember it. We were saying that it is some x alpha star when PCA we were saying, right, that W star is x alpha star and alpha was some constant. We were saying that we'll get that solution when it W star was a linear combination of all the data points, right? That was and here also I am getting this similar kind of understanding. Only thing is here it is involved with some labels, right? Just give me a minute. I hope this is fine. Huh?
Yes.
Yes.
Until this point of time, everything is clear, right? There
Yes,
is no
sir.
issues with that.
Yes.
Maybe you wanted to see that. Okay, so according to the lectures, right? This point I should be showing you that uh, the geometrical interpretation. So let's see the geometrical interpretation. Actually, I have just jumped a little bit. So we were thinking about what, like, whether it is computational intensive or not. But okay, we'll come to that point later. Shall we see that whether how it will look like in a space? Fine. Is that
Mm.
okay?
Yes.
So let us try to see, like, try to observe it through your uh, geometrical interpretation. Suppose okay, and we can visualize this using only 3 dimensions, right? We cannot, whatever our observations will be there in 3D or 2D, what we generally do, we try to extend it to our d-dimensional spaces. Fine, and we'll do the same here also. Suppose you have feature 1 and feature 2, right? This is feature space. Okay, what is feature 1 and feature? How this data was looking like? I said initially, right? Was this data looking like this? Is that fine? And we had corresponding labels here. That was y1, y2 to yn. That was my y feature, y vector. Is that correct?
Yes.
Uh, this data is of what dimensions? Here D is what?
Two.
2, right? F1 and
Oh,
F2.
F2
And
features.
n equal to, I don't know.
Number of
Equal
Like,
features.
to
here, and let's say
data points.
whatever actually sir has used, right? So I'll use that one, y1, y2, and y3, only 3. So n equal to 3. We'll try to actually visualize these things, right? So suppose this is height and this is weight. What does that mean? The space actually given by this all of f1 and f2, right? So f1 is, let's say, height, and f2 is weight. So where these data points will lie, actually, can you just try to imagine this? Where x1, x2 will lie?
F1, F2 plane.
F1, F2 plane, right? So that entire plane will have this x1, x2, and also what it will have? All the linear combinations of it. Is that correct?
Mm.
Yes.
So
Yes.
basically this will be some plane, right? And all the values will be its what? The linear combinations of it, right? So basically it is kind of like that. Okay, where is this y vector will lie? If, let us say, if this y vector lies into this plane, we'll get a solution, right? That is our basic understanding of linear algebra. Is that fine? But let us say if it is not in the plane, if it is, let's say, outside of the plane, what you do generally?
Take a
You
project.
project it onto that plane, right? And we'll find out its projection. That will give me that. Will that be a our correct answer, or it will be a like approximate answer? Yeah,
Not
with some right. Yeah,
Approximate.
I think in MLF lectures I have like explained it like little bit maybe in the depth, but I don't know how many of you have watched that. But say that, and this will be the projection will always be perpendicular onto that plane, right? Is that correct? Okay.
Yes.
And
Yes.
what how what this data will look like now? Can it look like X transpose alpha star?
X transpose W.
Alpha star. W we don't know. W we said like it's a solution, right? Correct. I'm just saying that it is a solution. I'm just saying that there exists some alpha star, uh, which actually happen to be like it should be equal to W star to get my solution. But let us try to say that this is not W star. This is some other solution. Fine. Is it okay? I'm just saying it like currently. We'll
So
try
what
to
is alpha star here?
yeah, alpha star is like same as it. W star was like it was W1 star, W2 star. These are the coefficients, right? Similar
Mm-hmm.
coefficient is there. How this matrix will look like now? Here it will be F1. Okay. So if I'm trying to just saying that it is F1 and it is F2, and here you have alpha 1 star, alpha 2 star. Fine. So basically this multiplication will be what?
F1 into alpha 1.
Can I say that X transpose alpha 1 alpha star? So alpha star will be basically the vector of alpha 1 star, alpha 2 star. X transpose, I can say X transpose, right?
Yes, sir.
You'll be able to visualize this. So basically F1, F2, these vectors, if I wanted to write it, they will like same as sort of this one, right? X1 transpose, or maybe I don't know, something like that, right? Why?
N cross D matrix.
Correct, na?
Yes, sir.
What is X vector here? X1 vector, these 2 points, right? X1 basically is R2. Correct, na? I hope you guys are able to like able to
X is a D cross N matrix. X transpose is N cross D matrix.
correct, right? And can I say that this should be that combination X transpose alpha star in that plane?
Yes, sir.
I'm just saying that. Okay, let us say I'm just saying that this will be the correct answer. So in that case, how this will look like? This projection will look like. Let us try to see that. This is y, right? This y vector. Its projection onto the plane is X transpose alpha star, right? And what will be this error? This will be the error, right? Correct.
Yes, sir.
And what this error will be? How it will look like? Y minus,
Y minus X transpose alpha star.
and basically this error vector is here, na? Correct. Correct, right? Is that correct?
Yes, sir.
Vector multiply or like vector subtraction, right? If you just subtract this, you'll get that point. And can I say that this error vector is perpendicular to this? See, okay, if you are not able to
Yes.
understand this part, here also you can see this error vector is perpendicular to X transpose alpha star.
Alpha star.
So when it is perpendicular to X transpose alpha star, that means if you
Orthogonal.
this is or these 2 vectors are orthogonal. So X transpose alpha star is also vector. These 2 vectors are orthogonal. So by orthogonality, what I can say about it, y minus X transpose alpha star
Dot.
transpose. Yeah. So
Into
in the dot product, basically, I write like in terms of transpose
Yes.
X transpose alpha star. Is that fine? And that should be equal to
0.
0 because these 2 vectors are orthogonal to each other. So can you just expand it now? What it will be now? Y transpose minus what is it, x transpose, or so transpose become x, right? X alpha star. Alpha star basically is a constant, right? So we don't have to worry about it. Or maybe, okay, no, it's not a constant, it's a vector, right? This will be like this, alpha star transpose x. Is that correct? This part
Yes, sir.
into x transpose
X
alpha.
transpose alpha star.
And if you do just like basic multiplication, it will be what? Y transpose x transpose alpha star minus alpha star transpose x transpose alpha star. Is that
Alpha
fine?
star.
And that should be equal to 0. Is that correct?
Yes, sir.
So, and what was our W star? This part, right? X transpose pseudo inverse into xy, right? So I'm just writing it down again. So W star was my solution. It was x transpose pseudo inverse, right? Okay, I'll just not write pseudo inverse, and maybe I'll write only normal inverse to understand. Pseudo inverse xy. Is that okay? So if I say that this is a solution, that means it should be able to satisfy this equation also, right? This solution. So I'm just saying that it should be equal to alpha star. So that means if I just substitute this part here, it should be equal to uh, satisfy that part, right? So that should be giving me the value 0, right? Correct, na?
Yes, sir.
This W star should be a solution. That means that alpha star should be in a plane, right? Correct. That x transpose alpha star should be in that plane. Is that correct? Then only I'll get the equation, right? This is column space of, if you remember that part, like uh, if I wanted to solve a linear equation, that what does that mean? I will solve ax equal to b, and that b vector should be in a column space of A. This is the same thing we are actually doing. Okay, so what does that mean? I'll just try to substitute that part here. It will be y transpose x transpose. What is alpha star? So I'm just substituting w star here, and that w star will be x transpose inverse
XY.
xy minus x
Y
transpose inverse xy
the whole
transpose,
transpose.
right, into x transpose to x transpose inverse xy. Is that correct? Okay, let's try to find out its values. So okay,
Y transpose X transpose inverse.
where
X
is it?
transpose in
This, let's say if I keep it like this, but about these terms, what will happen to it?
Y transpose X transpose.
Y transpose x
X
transpose
transpose.
x transpose inverse transpose, right, into x transpose. Is that
Or
fine?
transpose inverse also you can write, no?
Okay, let's say transpose of inverse. Okay, I don't, that's fine, right? So it's kind of same, I guess. Okay, what is the next part? Here it is x transpose inverse and xy, right? I think basically this will give I, right? Identity matrix.
Yes.
Yes.
So if I just remove this part, is that okay? If removing means like, because this gives me identity matrix, this will look like this, right?
Yes,
Is that
sir.
correct?
Yes, sir.
You will be able to see. Okay,
X transpose X.
huh?
The inside bracket part.
But this should be equal to same, right? Did I do some mistake somewhere? Because this quantity and this quantity should be equal, so that I can be able to show that this part equal to 0, and then that I can say that this W star will be the solution, right? Okay, I don't know, somewhere I did mistake.
So
Hmm.
X transpose, the whole transpose is same as X transpose. And isn't it middle part? X transpose, the whole transpose.
Yeah, I think it's a symmetric matrix, right?
Yeah,
Okay.
yeah.
Yeah, yeah,
Yes,
yeah.
sir.
Okay, I think, yeah, correct, correct. So actually XX transpose is a symmetric matrix, na? Okay, and the transpose of the symmetric matrix is the same as that of
Same as
Same
the
matrix.
same matrix. Okay, okay. So that means it's correct. So basically you can see that this quantity here and this quantity here is equal,
Same.
and that means I'm getting the 0. That means here I can say that LHS equal to RHS, and that again same thing is, that means this is a solution to my problem,
Solution.
right? And that is, we actually solved it through geometrical interpretation. Okay, I think that's the part. Until this part is, everything is clear, right? I hope no issues
Yes.
with this part. Okay, good. So what is W star? I said. So what is our solution? XX transpose.
XX transpose inverse
Yeah. So okay, inverse. Right, let's say inverse XY.
XY.
Okay. And what issue it will have? I said computational issue, right?
Yes, sir.
Is that
B
correct?
cross D matrix.
Because
B cross D matrix.
yeah. So if you have a computational issue, uh, what we can do now? We'll use
X transpose X. X transpose X.
no, not we cannot do, like we have done that for PCA, right? We are not doing that same thing here. What we can do instead is, we'll use the method
Gradient.
called gradient descent, right? Gradient descent to solve this problem, because I know that W star value is like this. So if I directly compute, right, using the computer, I should get the W star. But again, this will be a, you know, very tough computations, or maybe expensive computations. Like, that's why what we can do is, we'll use the gradient descent method. What is the gradient descent method? W2 plus 1. I hope everyone is aware of this.
Yeah. WT
It
minus
minus
eta t
Eta
T and gradient.
gradient.
F calculated at WT.
Yeah.
Gradient of F calculated at WT.
Okay, at WT. Right. So I'll say that WT here. Is that fine? You can use T up and below. That's fine. Like however you want to do. Uh, okay, that's fine, right? So basically, I will do that. Okay. Now, if I wanted to use the gradient descent method, what was f of w? It was norm of,
minus y.
X transpose W minus Y.
right? And I think we have calculated already what is del f w, right? And it was 2.
2
2 x,
into
x
X
transpose x
transpose
minus 2xy.
inverse.
Not inverse.
Inverse. No,
No.
you're not inverse.
That was w star, the final solution, right? Del f w. I think initially we have seen that when we are equating it to 0, right? I don't know where. Here, this portion.
Yes, sir.
Okay, so I'm using that part here again. So that's what my del f of w is there. That means gradient is there. So how this gradient descent rule will be useful? So wt plus 1 equal to wt minus eta t into 2 times,
2 XX
or maybe I'll just
XX transpose.
2 into xx transpose w minus 2 xy, right? Okay. So, okay. So what we have achieved here, we need not to do the calculations for inverse, right? In W star, we wanted to do the inverse calculations, and inverse, actually here in this case, inverse calculations are tough to do, right? So that's why we had tried to achieve this part. But again, this part is having one problem. That was what we have discussed already. This solution will also, we need to compute this, right? XX transpose. And when XX, what is the dimension of XX transpose? D
D
cross
D
D.
cross D.
D cross D.
X is in D, right? So okay, X is in, what is it?
And it,
Cross N and
X.
N cross D. Okay. So let us say you have D cross D, right? So D cross D it will be, or N cross D?
D cross D, sir. XX transpose will be D cross D.
X will be D cross N. Okay, fine. Okay, I think sir has said it's N is large. Okay, fine. So let us say if it is like the dimensions are large, right? I don't know. We
For calculation of every number of the matrix, you have to do n calculations.
Yeah, correct. So here, yeah, correct, correct. So here, what was the issue? This order was like even larger, right? Because inverse computation, you have to find first XX transpose and you have to take the inverse, right? It will again inverse lot of uh, steps, right? To do first, you have to calculate XX transpose and then you have to calculate its inverse. So that's why we use gradient descent. But in the gradient descent also, you will have to at each step you have to do this calculation, right? XX transpose. Still, it is better than the inverse calculations, but still it involves like if n is large, it will have like again more calculations, right? We need to do it is again computationally expensive. In that case, what we do, we use
Stochastic
yeah,
gradients.
stochastic gradient descent. What is that? Batch wise, right? So you can actually in like lot of outside maybe papers or somewhere, stochastic basically they will say that uh, each batch will contain only one data point, right? So or but basically here in this case it is there are two ways actually. If you say that stochastic, they will say that each batch will contain one data point, or there is a batch gradient descent which says that there is a bunch of data points will take like out of n data points, right, for the calculations. Here the when I said stochastic gradient descent, I'm just referring it to the second one, which is like we are actually taking the batch. What is that I mean by batches? You have n data points, right? uh, right? We have the n data points. We don't compute x6 transpose for all n data points. What you do is you take few data points, right, out of this n data points randomly. You select a few data points out of this n randomly, and you do the calculations for that, right? So the stochastic gradient descent is like the same. You just you do the iterations. You know that gradient descent is a iterative algorithm, right? All of you are aware of the gradient descent? I hope yes. If you are doing MLF and MLT simultaneously, in that case, I think gradient descent will come in week 8. So I don't know if you are okay, fine. But somewhere you have heard about this, right? The gradient descent method. I'm assuming that you are doing, you know that. So what you do is at each step, you sample some data points, right? And you sample it at uniformly random, and you perform the uh, you perform your gradient descent on each of this uh, data set, like each of that bunch of data set. You're understanding the point, right? You have 1 2 3 4, let's say n examples. Let's say what you do is you just take, let's say, few data points randomly, let's say selected randomly, and you perform the gradient descent operations only onto this. So what will happen now? You don't have to do the n cross n n calculations for each time, right? For that x6 transpose. Fine. So basically, you are doing this. What is this part? This is like this part, right? This part, this portion, gradient. Okay, what is that tilde? That sign? We are not using entire data set as such. What we are using is like smaller data set
Sample.
out of, yeah, smaller data set out of it, and we'll perform the gradient descent on each of it, right? And after t rounds, we'll get some w star, right? And what this w star will look like? Actually, we'll take the average of all this wt. Okay, say I equal to 1 to t. Here it should be equal to t
WI.
wi, right? Okay, and this w star will not be exactly equal to what w star we are having, right? It will have some errors, correct? And because how the sampling is done based on that, and that is called uh, stochastic gradient descent. This will not be exactly equal to the whatever solution we wanted, right? Is that correct? Because it will contain some error. This will not be exactly equal to this w star. It is, but it is better than the uh, like why it is better, because it will be very nearer to exact our solution w star. It is not equal to w star, but still we'll use that. Why? Because it is computationally like very much cheaper than the previous one. Is that fine? That this part is fine,
Yes.
right? Yeah, you don't have to worry about that much here, but you just try to understand that is like stochastic gradient descent is a very common method, like everywhere we use. Okay, that is fine. So let us say that is the part whatever we learned till now for you know this whatever we have learned for linear regression, right? We started our discussion on this, and we have end up with solution which is w star equal to x6 transpose inverse xy, right? That was my solution. It was computationally cheaper to find out the inverse of this problem. So what we try to understand is we'll try to achieve that solution using the gradient descent method. Now that is fine. What about nonlinear regression? Right, now we have just learned about linear regression. What about nonlinear regression? What do you mean by nonlinear regression? Until now what we are assuming is that the data point, whatever data points we are having, right, so they will contain the features, right, d features. What we are assuming till now is these features will have the linear relationship among themselves, right? Correct. We were trying to say that we are assuming that they are the linear features, but suppose these features are not linear, right? uh, what will you do now? Hmm?
Kernel.
Yeah, so the same thing we have done for the PCA, right, where we were saying that these features were in high dimensions. We use the kernel regression, sorry, kernel PCA there. But the idea of kernel regression in this nonlinear case will be little bit different.
Polynomial regression.
Not polynomial regression. It's like same linear regression only, but yeah, yeah, okay, you can say so. Like I think polynomial, so I can say yeah, that's fine. But how to achieve that part, right? So,
Feature extractor.
so you had that W star as X alpha star. Is that fine? Is that correct? In PCA. when we say that that part in the PCA, that time we said it should be equal. This W star is a linear combinations of all data points, right? Here also will be the same thing, right? Even my W star, let us say my W star uh, is we wanted my W star to be on the plane, right, which contains the features. Is that correct? Is that correct? But what is my solution now? X transpose inverse xy. I hope you are able to understand this. I'm just keeping some part which is not in the lectures, but you may go through the lectures once again and you might be able to connect it. But this is the scenario, right? I wanted my W star to be in a plane so that I can be able to. So if you just try to understand this, the same diagram is there, but what I'm saying is my W star should be in the plane containing all data points, right? Then I'll be able to get the solution. Fine. I'm using that result to correlate here. So that means x alpha star should be equal to x transpose
X transpose inverse.
xy. Okay. And suppose if I pre-multiply this part by x transpose, what I'll get? X transpose x transpose inverse xy, right? Now this part will be equal to
Identity.
identity,
Identity.
or it will get cancelled, right? I'll say. And what is this part now? Here, if I rearrange the terms, it will be x, suppose x transpose x alpha star, okay, will be equal to xy.
X
Is that okay?
X will get cancelled.
Right. Uh, I will not cancel it as of now. Okay. Uh, what I'll do is instead, this is the part, right? So, okay, no,
X should get
okay,
cancelled, right? Sir?
I'll do one thing. No, this is not the our linear algebra, right? It's a matrix, right? These two matrices are there. How the matrix will not get cancelled like that, right? It's not like that. You have to multiply with inverse. Is that correct? This is not
But
like
X transpose X we can multiply, na? X transpose X, it is associative, na? Matrix multiplication is associative. So we can multiply X transpose X first.
no. Until now, okay, that is okay. I don't want to do that. So you can do it. I understand. I understand that part. You can get it cancelled, but I don't want to get it cancelled. So keeping it like this. So x transpose x alpha star equal to xy. That's fine. This part is fine.
Yes, sir.
Okay. Now what we do is, let us say I'll just multiply one more time with uh, x transpose here. Is that fine? Okay.
Yes, sir.
Now what I'm saying is, this is x transpose x, and this is uh, x transpose,
X transpose X, sir.
yeah, x transpose x, right? And this x transpose x into x transpose x will be basically what? Can it be
X
square
transpose X whole square
Whole square.
square alpha star? Is that fine? It should be equal
equal to
to
X
x
X
transpose
star
x y.
into Y.
Okay. Now I'm just saying that consider this x transpose x as k. Fine. So what I'll get here is k square alpha
Alpha
star
star.
equal to ky, right? And or will not, let us say you wanted to cancel it out. So what you will do here, you'll just multiply both the sides by, first I'll do one by one. Okay, simple. I'll just do some simple steps here. Got x transpose x into x transpose x alpha star, right? I'll multiply this equation by x transpose x inverse. So if I do that, what I'll have, what I'll get? Is that okay if I write it directly? So x transpose x alpha star will be equal to y. Fine. And
Yes.
alpha star will be equal to x transpose x inverse y.
Right.
And I'm just saying that is x transpose x will be equal to k. So alpha star will be equal to k inverse y. Is that fine?
Yes.
Yes, sir.
And this k is called as a that is a kernel matrix. And what will be the dimensions of this kernel matrix?
N into N.
And cross M.
N cross n, right? That's fine. All of you are okay with that this part?
Yes, sir.
Okay. So now that was the part which actually I wanted in a training set. So what will happen in the test if I wanted to do the prediction, right? That is our goal to predict. So during prediction, what should I do? Uh, so let's say your x test is there. So test data point is there and which belongs to d dimensions. What will happen in this case? So basically whatever your w star will be there, right? The w star transpose x test, right? Generally you wanted in x test, but suppose you wanted to do that in the higher dimensions. What do you do then? Phi of x test, right? We are actually not trying to solve this w star. The problem will be like this now. Like we wanted to find the minimum of phi of xi minus yi square. Is that okay? Previously we are actually solving the different problem. Now since it is a linear regression the non-linear regression problem, we are actually solving it in a higher dimensions now, right? But we are
So
actually
W star T phi x test
Hmm.
will be the predicted value of pi x test
Correct.
of
For
right.
x test, that is correct, that is correct, that is for like we wanted to check for that prediction, right? This is my prediction, the final prediction, right?
Okay. Okay.
Correct. So what it will be then? What is w star t here in this case? It will be summation of I equal to, let's say 1 to n, and I say alpha I into phi of xi, alpha I star, let's say. I hope you guys are able to understand this part. Why I'm
Yes, sir.
writing this? Huh? This is w only, right? I said w
Yes,
is
sir.
x alpha star, so I'm just using that, and here it is phi of x test. I hope this is okay. I'm not doing anything new. I'm just like just putting the things there itself. Okay. Okay. But I will not be able to calculate everything here because it is in the higher dimensions. What should I do instead? I'll try to uh, I'll try to rearrange these terms. Can I rearrange this in this manner? Alpha I star. What this part will be then? Phi of xi. Uh,
Pi of xi transpose pi of x test.
what is this? First place, this is the kernel matrix. What does that kernel matrix? If you remember from PCA, what does that kernel do there? Kernel function
Kernel
do
is
there.
just a function of xi
Yeah.
and x test, right?
Yeah. So
Kernel
here,
is
what it is trying to do? Here it is trying to find out the similarity between each of the data point in the higher dimension with respect to each of the data
x
point in
test.
the test, right? You're you know, okay, maybe will try to see from the PCA what you used to do. You had data points, right? X1 up to, let's say, there what you do generally, x1 and x2, you had data points. You you are trying to map it to the higher dimensions, right? There, and you pass it, because we wanted to find out that this part phi of x1 into transpose into phi of x2. So instead of doing that, what you used to do, if you remember this diagram there, what you used to do, you used to find, like, you had like some kernel function which gives me uh,
xi x2.
sorry, x1 x2, right? Correct, right? I need not to explicitly do this calculation,
Calculate the phi.
right?
Calculate. You don't need to calculate the
Yeah,
phi.
I used to use the function to calculate this quantity, because this quantity is the same as that of what you calculate like this, right? If you remember that part, right? Similarly, I don't see multiplying all of this, it will be again computationally very expensive. What you do instead, you use the kernel function to get all of these values. But here, what values you need here? So there, you didn't have any test data point and all, right? Like at the starting point, starting terms. Here, what you do is you will try to find out the similarity between each of the data point, right? Between, let's say, here the kernel function will give you the value of x phi of x1 and phi of x test, phi of x1 x2 and phi of x test, like that. Correct, right? And alpha I will give you what? Basically, it gives. So let us say this will give me the
Some coefficients.
this is similarity gives me, right? It gives me this how similar my x test is from the each of the data points. So let's say you have 10 data points in your data set, and you have new data point x test, right? So in higher dimension, how much similar they are to each other. Fine, that gives me that part. But alpha I star actually
Contribution of each point to
yeah,
the
contribution of each of these similarities towards my final solution, right? That that actually works like a kind of a w, right? Like, I hope you are understanding. uh, Generally in linear regression, what was our how do you find out the solution? Linear regression, okay, don't worry about non-linear. How you do the prediction here in linear regression? You'll have this w star, right? And if you have some test data point, what you do there? W stars are what? They are kind of weights, right?
yes.
And X test will contain, uh, it is a vector and it will have the features, right? Uh, you are not okay. Maybe we'll try to understand that. Okay, what is X test will look like? I'm talking about now linear regression perspective. Okay, we are not talking about non-linear right now. What is X test will contain? Can I say them like x1 test, x2 test? What are these values? These are the some values of the data points, like feature wise, right?
XD, no, sir, it will contain
Sorry,
D.
not N, D, right? Is that fine? And how
Yes,
will
sir.
you predict now? Basically, you will take the W star, which was my the best possible solution, and you will multiply with, correct?
XD. Yes, sir.
And W star will contain what? Like W1 star.
W2.
Can I say that like
WD.
uh, x1
W1 to WD.
x1 test plus W2 star? That will be my like. I'm just writing it down here for you till star,
D.
right? So here, what do you, what is W1 W2 W2 D here? They are
Components of
actually,
W star.
yeah, that is the components. But what they are actually doing here, they are giving me the weight, like how much this each of this feature
Will change
will,
after the output.
correct, right? So how, like they are weighted average, right? Weighted average across that vector x test. Fine. So how much that contribution should be there from that x1 test or x2 test? Are you able to visualize in the higher dimensions?
Yes, sir.
All of you, you're understanding? W1 star actually gives, like, whatever the W star, actually it gives me like, let's say this will become, it will look like this, right? 0.2 times x1 test. Okay, test, I'll denote it by, let's say, t, plus 0.3 x2 t plus 0.4 x3t plus 0.05 x4 t plus, let's say, up to 0.0001 xnt. What does that mean now? xdt. What is happening here? So this is having more weight, right? So this feature is very important, right? x3t is feature important from the prediction point of view. x3t will not be that important feature, right? And how this, like, this is able to understand, like, we are able to understand once we optimize that solution, right? We optimize that solution and we get some W star, and the W star will look like this, right? 0.2, 0.3, 0.05, 05, and like that, 0.000. Fine? Is it fine? So W star actually keeping a tab on how much each feature will contribute towards my prediction. Is that correct?
Yes, sir.
Yes.
So that's what it was doing in the linear regression case. In non-linear regression case, this is not X test. This is because it's not linear, right? It's like higher dimension space than the uh, uh, like for the same data point, right? So we are actually wanted that W star which keeps that, and that's what we have started here, right? I think somewhere here, yeah. But this W star, what we said is this W star is some combination of data points like alpha I star, phi of x star. So now this alpha I star actually doing the same work as that of W star, but in a different manner, right? Now the kernel function, what does it do? It actually finds the similarity between the points, right? But let us say if it is highly similar, right? These data points are highly similar, but uh, this will actually keep, like, if the weightage is low, then that means the contribution to that point, right, is lower. Is that fine? Are you able to like uh, relate it little bit?
Yes, sir.
I don't know. Okay, so it might be like maybe I'm not explaining well, but that is the, and how, from where this alpha is coming from here, right? So how will you get that alpha star, basically alpha star? This alpha star actually, that also we can get it from here, k inverse y. So we'll find out the kernel matrix. How to find out the kernel matrix?
X transpose X.
So kernel matrix will be basically
X transpose X or
phi of, can I say phi of
X transpose phi of X.
x transpose or phi of x transpose,
Phi of X transpose phi of X. Phi
right?
of
Na?
X transpose phi of
Phi
X.
of
Yes.
x, but we are not explicitly doing that. So actually we wanted to achieve this. We are using like kernel function which gives
But
me
we
that,
use a function to calculate that.
right? No? Yeah. Now, and that function, once you calculate that kernel you have found out, using that kernel and this labels, you can get alpha star, which actually kind of uh, gives you the weighted sum of this, right? There's sum of all the similarities with respect to my alpha, right? So this gives me the weighted sum basically in the higher dimensions. I don't know, like, if you are not able to understand, maybe you can go through the lecture once, but this is how it is working. So, like, imagining it in the higher dimensions is little bit tricky sometimes, right? Okay. Okay, so let us move towards the last part of this. So we have learned what last time. We have gone through the method called maximum likelihood, if you remember it. Is that fine? We
Yes, sir.
have, yeah. So what was that method and why we use that method?
To find the parameter
estimation,
Okay.
right?
You estimate the parameter.
Yeah. So yeah. So actually, we wanted to estimate the parameter. Okay. Now we'll try to see this in the probabilistic view for linear regression, and we'll use the same method to estimate the parameter. What was our x in d dimensions? Your y is in one
Or
dimension, right? So, and you have how this your data set will look like that, right? It will be like pairwise, right? X n, y n. I can actually write our data set in a set like this. Fine. I hope this is
here,
okay.
x1 is a vector and y1 is
Yeah,
scalar.
y1 is a scalar. Yeah, right. This is okay.
Yes, sir.
So what we are saying is, I given a sample, we will try to find out given a sample x, what is the label, right? If I wanted to say in that view, given a sample x, what is the distribution of y? Let us say, I'm just saying that given a sample x, what is the distribution of y? In that case, how will it look like? So okay, I'll just try to we'll try to visualize in 2D. So you have, let's say, x and you have y. You have these data points. Uh, what is this? Let's say this is x1, y1. Where is x1? This is x1, right? And this is y1, correct? This is, let's say, x2, y2. This is, say, x3, y3. Maybe I'll not use a lot of data points. I'll just use some to not, uh, you know where is x3 and y3 is there, right? On 4, y4 and x5, y5. Is that fine? Where is each x1 and y1 or x2 and y2 lies, you understand, right? This is x2, x3, this is x4. Fine. I'll just not use it now. Okay. Suppose I try to fit the line here. This, what is the equation of this line? Can I say it is W transpose X? Huh? Is that
Plus
correct?
some constant. Plus some constant.
Leave about the constant right now.
It is not passing through the
Yeah.
origin, sir.
Okay. Think about like it is passing through the origin. Okay, I'll just. This is okay. Suppose this is W transpose X. Basically, this is WX, right? XW, something like that. You just think this as like W transpose X. Uh, W transpose. What is this data point is? What is this data point? Can I say it is x1, comma? Can I say W transpose x1?
Yes, sir.
Is that fine? All of you are okay with that part?
Yes, sir.
What about this data point?
W transpose X.
x2, comma?
Mm.
x2, comma?
W transpose X2.
So what about this? x3, comma?
X3. W
W
transpose
transpose
X.
x3.
Here x4, W transpose x4, like that, right? So, but is it equal to y or y1
No,
or y2 or y3?
no, no,
Right?
no.
Sir.
So when this will become y equal to y1, so W transpose x1 plus some error is there, right? Is that okay? And that should be equal to y1, right?
Yes, sir.
And y2 will be equal to W transpose x2 plus some error. W3 equal to W transpose x3 plus some error. Is that fine?
Yes, sir.
Okay. So what we are saying in probabilistic view is, we are saying that suppose I have given a sample of data points like x data points, and I'll try to uh, see what is the distribution of y. So can it will be looking like this, W transpose x, or maybe W transpose x plus epsilon, some error. Maybe it is a vector. right? That's okay. So there is some error, or we call it as a noise, right? What we are saying is, this is the problem, right? This is the problem in our hand. Given a data, given the set of data points, can we say something about our labels? Is that fine? This distribution is okay, looks okay.
Yes, sir.
And I'm just assuming that for now, that this noise is Gaussian distributed. What does that mean? Each of this epsilon 1, epsilon 2, and epsilon 3, we are picking it from which distribution? The Gaussian distribution with mean 0 and variance sigma square. Fine. That is my assumption right now. Right. So this is the assumption that the errors are normally distributed. Is that okay? I hope that's fine. Any doubt is there, you can just like ask me. That's not a problem. Okay. I'm not like assuming that. So W transpose x1 plus epsilon, right? Here x is a constant, or x is a constant in the sense x I know, right? This is the known quantity to me, right? Epsilon is Gaussian distributed with right, and this is the part which I don't know, right? The unknown. Unknown. This is unknown, but is this fixed? This is a random variable, right? Kind of a random variable right now.
Which you are trying to estimate.
Yeah, and this like we will try to estimate that part, right? But what cumulatively, what will be its distribution? Can I say it's normally distributed with? So basically, what I'm saying here, you if you try to understand is, I hope this is fine. If you are okay with that part, or basically if you are not understanding this part also is fine. We are trying to estimate what here, which parameter we are trying to estimate. If not, this is fine, but we are
W
trying
you
to
are trying
estimate
to
for
estimate.
W, right? So what is the method we use generally?
Maximum likelihood.
Maximum likelihood. Okay. So if, can I say that W transpose X will be some kind of constant? Even I don't know what is W is, but this multiplication will go into some constant.
Yes, sir.
Hmm? Because that is some value, right? That's what we have started, and like you can do the any matrix multiplication here that actually throws me some value that is a scalar quantity. If my epsilon is normally distributed with mean 0 and variance sigma square, so if you remember it from stats, right, how what will happen to the mean of the normal distribution or any distribution, if let's say if I add some constant to it,
Mean will shift. Mean will shift.
so how much it will shift here in this case,
W transpose X.
right? And that means this distribution will be normal W transpose X sigma square, right? Now, is it fine? So y given X, that means given a sample points, sample data points, what is the distribution of y? If I try to calculate with assumption that the errors are normally distributed, this is what my distribution will look like, right? So what is to be so assume that sigma square is known to me. I don't know what here, which parameter I don't know here, W,
W.
right? So how to estimate this parameter W? Using the
Maximum likelihood.
maximum likelihood estimate, right? Okay. So yeah, now what you do generally in maximum likelihood, we'll find out the likelihood.
Product of the
So
probabilities.
we wanted to find likelihood of W, and
Given
given what?
Y1, Y2.
X1, X1 to Xn we know, right? And Y1.
Y1 here, sir. Okay, yes, okay. Yes,
We
yes.
know X also and we know Y. So given X and Y, right?
Yes, sir.
And what it will be? It's a product of
Probably the densities.
To 1 to how many? N or D? N.
N.
For n
And
sample points. And what is the density here? It's Gaussian density or normal distribution. It will be e to the
1 by
power.
2 root
Okay, 1 upon 2, 2 pi,
Square root.
sigma
2
square.
pi sigma, right? 1 upon
Yeah.
root 2 pi sigma.
E
Uh,
raised to power.
E power
okay, e to the power
minus x
minus,
minus
what is it here?
W
x
transpose
So
X
W
minus
I
transpose xi, right?
minus
Minus
X I. X I.
and yi.
no, that is the mu, right? Yeah.
Just look at it. Look at it once more. Uh,
2.
is it correct?
Yes,
2
sir. 2,
sigma.
2
Okay,
sigmas.
2 sigma square. Sorry. But this part you understand, right? W transpose xi minus yi.
Yes, sir.
Yeah.
Yes.
The mu is W transpose xi.
Correct, na? Because this is the mean here. Okay. Fine. Okay. So, and what is the next step?
Take the logs.
So basically, can I ignore this here? What are the constants here? This part is
Sigma.
constant, right? This
Root
also is some constant.
pi.
So if I ignore
Yes.
it now, this step also is fine, and then my equation will become pi like a product of I equal to 1 to n, basically e to the power minus. Can I say that?
W transpose Xi minus I.
Okay. So okay, basically next step should be equal to log L, right? Take the logarithm thing. So what is the log likelihood here?
Minus of
So
W
I'll say that
transpose.
it will
Log
become
will not be there.
sorry. Okay, the product, it will not be a product now. It will be your
Sum.
sum. What is the sum here? So basically treat it as a constant. So the sum will be what? Summation of I equal to 1 to n. Basically it should be equal to log of this constant, right? Plus log of so that will go away. So I'll remain with what? Summation of I equal to 1 to n minus W transpose xi minus yi square divided by the 2 sigma square, right?
Sir,
Hmm.
where this W transpose Xi minus Y? I mean, how
Okay,
this?
this is the density, right? W given x is the density, which is a normal density. Is that fine?
Yes, sir.
What is the distribution of that normal density?
So it should be Xi minus mu whole square.
Xi minus mu whole square.
Mu is W transpose X, right?
Okay,
Mu
Mu
is
is
W
what here?
transpose X.
This is
got
the mean, right?
got it, got it.
Now it's fine.
Yes, sir. Yes.
So this is okay. This part log L,
Yes, sir. Yes, sir.
right? So basically, I can actually ignore this term. So and I can actually ignore the constant term also, because if I differentiate it later, it will not of any use, right? Because it will go to 0. So uh, what will be log L final? Like basically, it will be summation of I equal to 1 to n minus W transpose xi minus yi square. Is that fine? And
Yes, sir.
what method are we using here?
Maximum likelihood.
Maximum
Yes.
likelihood, right? Is that
So to
correct?
maximize this.
Yes. We
So,
will minimize this because
so
negative sign.
yeah, if I use the maximum likelihood, so I can actually use, like, I can say that max of w, and this function will be the right minus which function I have to maximize? Summation of I equal to 1 to n minus of W transpose xi minus yi square. Uh, so I can actually maximize this function, or I can
Minimize.
or minimize W over this. What change it will have? It will not have that negative sign.
Negative sign.
You will just remain with this part. Okay. Okay. And the w hat ml with this part. Okay, how does this look like? Can you shall we try to visualize what is this look like, this equation? It will be
Squared error. Some squared
w1
error.
transpose x1 plus or minus y1 square plus, can I say that let's say w transpose x2 minus y2 square up to w transpose xn minus yn square, right? And if you try to minimize this, means what does that we have to do? D by dw of whole part, right? And we try to equate it to 0.
0.
So how does this will look? Can I say that it is 2 times w transpose x1 minus y1 into x1,
Yes. Chain rule.
and like that, right? So how this will look like at the end? So you can try it out. So I just expanded it till here. You can try it out later. This will be actually equal to w star inverse into xy. Fine. You can solve it later on. That's fine. Or if you don't solve it, it's fine, because this is the correct answer. This w hat ml actually is equal to xx transpose inverse xy, and that is equal to what? W star. And this w star, how we have calculated? We don't know that time, right? We didn't know that the error which we wanted to find, like the error is normally distributed, right? That was not the assumption that point of time, right? When we initially started, we just did, we tried to minimize that error, that h of xi minus yi square, using the optimization technique. That is like general techniques we use, right? Here probabilistically, if also you try to find out this w hat ml, right? That is actually coinciding with what? Our w star. And this has happened on the assumption of what?
Epsilon equal to normal
Right.
distribution.
So you can have any other distribution for your error, right? We have assumed that uh, the normal distribution or a zero mean Gaussian distribution. And if I assume the zero mean Gaussian distribution, the ML, like maximum likelihood predictor, will coincide to the actual linear regression solution. Is that correct? Why it is useful, we'll see it in week 6. But currently you just try to understand that if I, so let us say if I use some other metric here, maybe Laplacian noise, or if you say that it is, I'll use the Bernoulli distribution, what will happen to my, will that W hat ML will be the same or it will be different? That uh, it will be different, right? It will not be equal to the what equation we have got earlier. So this is one of the assumptions. I hope you know, like all of you all learned about linear regression at some point of time, and that there will be some assumptions. I think the uh, heteroscedasticity or normality of the errors. What does that mean, normality of errors? Like if you start with the saying that the errors or noise is follows the Gaussian distribution, right? Then your actual solution, the predicted solution or the maximum likelihood solution, will coincide with your your solution, which assumes that the errors, like the metric which we use, right? It was a squared error. So basically, if you assume the Laplacian noise, right? Uh, that means the noise is distributed according to a Laplace distribution. In that case, uh, the error will coincide with the assumption, or maybe you can say that if you take the absolute error value. So here we have taken the squared sum, right? Squared sum errors. If you take the absolute value for the errors, then your noise will be equal to Laplacian noise. Or if you take some other metric, right, you'll have that accordingly. It will have. But what is the use of this? We'll see it in the next week. Is that fine? I think,
Yes, sir.
yeah, maybe I'll
It
have
will
take,
get more clear when we
yeah, watch the
watch the
lecture.
lectures.
Yes, yes, yeah. Right, so
So when you suppose, so the error function will be different if you use a
yes,
different,
different assumption for the noise.
the loss function will be different
Yeah.
if you
So
use a
why,
different
yeah,
function.
why we seen that when we have the assumption for Gaussian noise, right? The loss function will be the squared sum loss function. If I use some other rate, it will be like change accordingly. Okay, but generally this will be a good assumption, right? Because generally we say that whatever happens in real life, it is
Is a
like
normal
normal
distribution.
distribution, and with that assumption, right, this is actually coinciding with the sum of square methods, and that gives me a better results. Then okay, so you can watch the lectures again and maybe you can get more clarity on that.
But
uh,
that normal distribution can have any mean. Na? It may not always have zero mean.
so
May
yeah,
not all.
yeah, so that is the important thing, right? So that is what, with zero mean, if you take, right, it will actually coincides with the actual solution. If you see the other mean, you'll get some difference. What will happen then? It will be again a normal distribution, right? Your y given x, but
Yes, it again will be a normal
with some
distribution.
constant, and again it will be, so what changes it will have if I have something else? Like here it will be w transpose x plus b, right? Is that correct?
W transpose X plus
So if I'm saying that
some constant
it's b, let's say it's constant b, then it will be w transpose x plus b, and then accordingly it will change.
minus Y1 minus Y1.
Yeah, so it will change a little bit, right? So it will just shift. It doesn't affect much, right? Okay, so I'll think somebody has asked me the questions. I'll have 10 minutes. Maybe you can just.
Yes, sir. In practice assignment,
Hmm.
question 5, 8, and 9.
Practice assignment. Okay. Question 5, 8, and 9. Okay, can you just give me 2 minutes? I'll just have water and come back. Hmm?
Yes, sir.
Yeah. Okay. Yeah. So question number 5, right? Consider a data set of heights of 300 individuals. The first 100 are drawn from the active pool of basketball players in the NBA. The next 100 are drawn from the list of chess grandmasters. Okay. The last 100 are drawn random from the city of Chennai. All 300 individuals are in the group of 2025. If you use a Gaussian mixture models to understand this data, what is a good choice of k? That is the number of mixtures. What do you think? How many mixtures is required? 3, right?
Yes, sir.
Why 3? You have like basketball players. You may wanted to group them like in a one group. Maybe chess grandmasters in one group, and like some 100 people or students who are from the city of Chennai, we wanted them into one group, right? So that,
Yes, sir. We can part all these three in three groups.
right, and that will be a good choice, right, for K number of mixtures. Is that fine?
Yes, sir.
Yeah, okay. That is the answer, right? It's like it's not
Sir, but
Answer given
answer
is
is
2.
2.
answer is two, huh?
Yes, sir.
Okay, why it should be three, right? Why two? It is like for 500 individuals.
Chess has nothing to do with the height, right? Similarly, basketball has something to do with the height. That's what logic I used.
No, no, but I don't. Is it?
Basketball players are generally taller.
Yeah, but
Right?
that is like we. That is kind of like we know it in prior, right? The prior information is there, and based on that information, I'm trying to assume it, right? Okay, Gaussian mixture model. What is the algorithm there we use? But that is not to do with this anything, right? EM algorithm. It's not okay. Okay, maybe I'll check and let you know. Okay, currently I'm thinking like it should be three, but I don't know why the two is. Maybe he's saying, but this is like kind of assuming something, right? If I see it, okay,
I
okay,
think Siddharth is correct, sir,
yeah,
because
possibility, yeah, whatever he's saying may be possibly correct, but I don't. Okay, I don't know what is the logic behind that. It's fine. It's okay. We'll see that. I'll check personally. If you maybe whatever he's saying is kind of correct, but I'll see it again. Maybe in next session or something. I'll try to answer you. What else is there? The
Okay,
similar.
sir, in question 8th and 9th also.
This is based on this data.
Yes, sir.
Based on which data is it given to you or no? Consider a histogram of million points, sample from GMO, three mixtures as shown in the below. Mixtures are labeled from left to right as 1 to 3. The mean of the mixture is 36. Okay. All the mixtures have unit variance. Okay. So for the first mixture might be minus 6 is the mean, right? No. Possibly 0 and 6. Okay. What is the mean of mixture 3? So what is the mean of mixture 3? 6, huh?
Yes, sir.
Okay. So
Yes,
which
sir.
of the following could be the values of pi 1, pi 2 and pi 3? So pi 1, pi 2 and pi 3. What is the
Pi 1
probability,
will
right?
be the
Higher.
largest. Pi 1
Yeah.
will be the largest.
And pi
Pi
3
1
will
is
be
largest, and then
pi
pi
3 will
2,
be
and
less.
then pi 1.
So which is the where is this will,
Third option, sir.
but this is I think it's a typo, right? Like pi 3 should be there, right? Here it's like pi 1 again.
Yes, sir. Yes, sir. There is a type in error
So what
here.
is the
That
answer? What is the answer to this question?
third option, sir. Third option should be the answer, and also the answer is third
Correct na.
option.
Yeah, this
Yes, sir.
what this was not your doubt.
No, sir. My doubt is on 8th and 9th.
Okay. If the point minus 3 is observed, what is the probability that it has come from mixture 2? Use the values of, okay, we have to use these values, right? Okay, and
Yes, sir.
minus 3 is where? Is somewhere here.
Yes, sir. It will be
And
in
what we
mixture
wanted to find is probability that it comes from mixture 2.
2. Yes,
Okay,
sir.
so you know what is the distribution? Is a Gaussian distribution, right?
Yes, sir.
With mean minus 6
Mixture.
and
Yes, sir.
variance 1,
Yes, sir.
right?
Yes, sir.
And then what is the probability that it comes from uh, mixture 2? So what will
Yes,
be the
sir.
probability? So total probability will be what? Basically it will be pi 1 into that probability, right? So e to the power minus something like that. What is the probability of, so first, okay, the first
1 by
mixture is mu 1 is minus 6, sigma 1 is 0, right? Sigma 1 square possibly, or sorry, 1. The second is mu 2 is how much it is? 0, square equal to sigma 2 square. Mu 3 is
6.
6 and sigma 3 square is 1. Is that right? And pi 1 is pi 2 is
Point seven.
pi
Pi
2,
1 is 0.7.
0.7, point 2, and
Point
point
2
one.
and point 1.
So
Point
given
two
the
and
point,
point two
what is the point given to me? X is equal to minus 3. So
minus
basically
three.
it will be, and we have to find out what is the probability that it comes from set
Mixture 2,
2.
that is pi 2.
So basically, what is the total probability? So like the divider is what, like, or denominator is what, equal to,
Total probability
yeah. So it will be point 0.7 into
into
e to the
e to
power,
the power minus x minus mu, that is
x
minus
is
3
minus 3
minus
plus
Minus
plus 6
square upon
divided by
2,
6 divided 2 sigma square
maybe
so
to 1
second,
here.
so it will be minus 3 minus 0, right?
point 3,
But okay, you are calculating the total probability. Okay, okay.
point 2 into e to the
Sir,
power. I'm
do,
calculating the denominator.
sir,
Okay,
don't we
okay.
have to multiply it with 1 by 2 root 1 by
It will get
root 2
cancelled.
pi?
Okay, I'll tell you. I'll tell you. Okay,
That will cancel
it
out.
will
That
get
will
cancelled
cancel
out,
out in
Okay,
the
it will
new.
be cancelled out
right?
on numerator from
So
numerator. Yeah,
yeah,
yeah, yes, I got
fine,
it.
no?
Yes, sir.
So I'm just like, actually I was writing the denominator part. So numerator will be just like single thing, right? It's like point 0.2
Yes, sir.
times.
It will be single
So
thing and
the
it
one,
contains that.
yeah. So it will
Yes.
be like minus 3 minus
Minus
0
0.
square upon 2 sigma square, which is like by 2, and 1 upon root 2 pi 1, like 1. So everybody, it will get cancelled. So in the denominator we will have zero point 0.7 e to the power minus 3 plus 6 square by 2 plus zero point 0.2 e to the power minus of minus 3 square by 2
Same numerator.
plus zero point 0.1 e to the power minus 3 minus 6 square by 2. So basically your answer should, like, will be zero point 0.2 e to the power, how much it is, minus,
Yes, sir. Now, sir, I get it. I will solve that.
all right, yeah.
Yes, sir.
And
Thank
this
you,
is
sir.
the probability that it will come from the mixture too. I don't know what is the answer.
Yes, sir.
It
The
will be,
answer is, sir, 0.22.
that is it. Ninth question, what is the problem? Assume that you are, same question or different.
No, sir. Ninth question is different from above
Okay, let's
questions.
say, assume that you are given a set of 10,000 data points in R. You fit a Gaussian mixture model with k equals to 2 for this data set using the EM algorithm, and it is initialized with mu1 equals to minus 1, mu2 equal to 1, pi 2, sigma 1 square, sigma 2 square. Okay. The estimated means are mu1 hat and mu2 hat for the two mixtures. Okay. A little while later, a domain expert comes and tells you that the data set given to you was actually sampled from a Gaussian with mean 0 and variance 1. Which of the following options is true? Okay. So basically, it is with the prior, right? Like if you are given the prior, so if the prior is the Gaussian prior, what will be its posterior density generally? I think it is somewhat like, maybe it is related to that, I feel. You are having mu1 as minus 1 and mu2 equals to 1, right?
Yes, sir.
And pi 1 pi 2, so same probability of, actually we are getting that cluster 1 and cluster 2, right? Pi 1 and pi 2
Yes,
equal to
sir.
1.
They have identical probability.
Variance also is kind of same, but
Yes,
the
sir.
thing is, you should be sampled, that sample comes from mean equal to 0 and variance equals to 1, right? So
Yes, sir.
and you said like mu1 equals to minus 1 and mu2 equals to 1. So EM algorithm, what do you think it will give to me? So mu1 is very close to mu2, but both are not close to 0. Mu1 hat is not close to mu2 hat, and okay, so for that, I think we'll have to look through, what is it? Which week is this? Week 4, huh?
Week 4, sir.
Where is that here? Algorithm. Okay.
Sir, it should be in the second file, that is GMM algorithm.
That one. But is with the prior, right? Is the prior covered here? I think it's
Yes, sir.
maybe
Prior is covered in MLF,
so.
MLL.
Okay. So with the prior, what will happen, right? So that is the question. Hmm. Okay. With the prior, what happens is your distribution like shifts, right? So if you try to understand this part, your mean is 0 and variance is 1. What will happen to it? I don't think it will shift anywhere, right? It will remain the same with the same mu height and mu 2 height, I guess.
Yes, sir. The right option is mu1 is not closer to mu2, and neither of them is close to
Close to
0.
0, right? Because it will like maybe the same cluster will happen, correct? Because if you add the Gaussian, like if you have the prior, what with the Gaussian
Okay,
prior, what will happen?
because the mean is 0, then because of that, it will neither shift from anywhere.
Yeah, yeah, that is true. But your posterior is equal to what? The
Alpha plus that number of ones, and beta plus number of zeros.
yeah, if your density initial density is Gaussian and your
Yes,
prior
sir.
is Gaussian, then what will be your posterior?
Yes, sir.
Huh?
It
Yeah,
will be,
maybe I'll try to see that. I am not
it will
sure.
be, I think so,
It's a
beta
conjugate prior,
distribution.
na? It's a
Yes, sir.
thing. Okay. So basically, it will be like e to the power. What is it? X minus mu upon sigma square. Suppose, right?
Yes, sir.
Into what is the prior?
Prior is, sir, Gaussian distribution.
But for let's say mu. Hmm?
Okay, sir.
So what will be the Gaussian distribution in that case? It will be 1 upon root 2 pi. Uh,
Sigma.
Sigma is basically 1, right? In that case,
Yes, sir. Sigma is 1.
to the power.
Mu is given as minus, mu1 is given as -1, and mu2 is
No, no,
given
no,
as,
no, no. Prior. For prior is 0, right?
yes,
mu
sir.
is
For
0.
sample
Basically, prior
prior
is
is 0.
the it's like prior is a function of because we treat mu the
We
parameter
can,
which to be estimated as a variable,
yes, sir. We
right?
the data which we get from
Uh,
sample is considered to be as prior.
so 2, right here, like
Yes, sir.
so here it will be like I think if I'm not like wrong is right, your posterior will be same as that of this the Gaussian distribution. If I
Okay,
will
sir.
have to actually like solve it, and basically
Okay,
this will
sir. Okay, sir. I will try it.
yeah, this is like I think 2 sigma square something like that, and basically this will become constants, right? We don't have to worry about constant. It's mu upon 2 to the power minus mu by 2, right? And if I just
X by 2, sir, not mu by 2. X by 2.
no mu by 2 na here. Okay, so this prior is for what?
Okay.
Prior is for that we are treating actually this as variable na.
Okay, you are taking the mu this.
That's how it is, right? No.
Yes, sir.
So you can see here, this was like this was a distribution, right? For p to the power alpha minus 1 and 1 minus p to the power beta minus 1 by z. If and the with the beta prior, what you do is, so this is different than this, right? This was your Bernoulli distribution, and that was your prior. Prior is a function of that parameter, correct? So it should be a function of parameter. It shouldn't be a function of your uh, like data points, right, or samples. So if you remember the x1, let's say x1, x2, xn, if they are the IID x, right, with parameter some mu, and we what you say in generally, let's say, or p, right? So but we say that generally we for maximum likelihood estimate or uh, yeah, maximum likelihood estimate, we treat this p as a constant, this parameter as a constant. But in a Bayesian estimator, what you do is we try this like we don't think this as a constant. Instead we say that it is a variable and it is having some its own distribution. and this distribution comes from the like some prior experience we are having or prior information we are having, and it should be a function of something, right? So this is a distribution of x, correct? This is a distribution of x, and this is a distribution of that variable, uh, or the parameter which we wanted to estimate. You will have to like just go through it once, right? So I think that is correct. Whatever I written is correct. The only thing is how you multiply it, right? So this is like product of I equal to 1 to n. Basically here it is I
It will become n times of.
xi into 1. So what is it?
It will become n times of that
Actually,
because the power will be added in the product.
hmm?
The
Hmm.
power will add in the product.
So,
x1 plus
so it will
x2
be xi minus mu by 2, or can I say like let's try to minus xi plus mu by 2 minus mu by 2, huh?
Yes, sir.
Square, sir,
Uh,
square,
huh? Square, yeah,
square.
squares. Okay,
Whole,
but with that it will get cancelled, right? No, it should not be like that. See, this is how it will look like. I'll tell you how this
First the product will run over that. I think so, sir.
x1 minus mu square by 2, right, into x2 minus
minus mu
mu
by
square by 2. Like let us say 2, I'm just keeping it common. In that case, this will look like this. I'll tell you. This product, right? I'm just writing down this product. How this will look like is e to the power minus 1 by 2, let's say common. Here it is x1 minus mu square plus x2 minus mu square, right? Na?
Yes, sir. Yes, sir. It is. It
And
will be that this way.
right, plus x, like it will go up to xn minus mu whole square, and now you have e to the power mu minus mu square by 2, right? And now
Yes,
that
sir.
will get added. So basically, e to the power minus half, let's say minus half again common. So this basically will become x1 minus mu square plus x2 minus mu whole square plus xn minus mu whole square plus
Sir,
mu square by 2. So
it
plus
will
mu square.
become x1 plus x2 up to xn and minus n mu. No,
Uh,
actually, it is in whole square.
so e to the minus,
So
right? No, actually you can what you can do is you can uh, like expand each of the term, and if I expand, right, it will become x1 square plus x2 square up to xn square. So if I write it down in a compact way, right, it will become summation of uh, I equal to 1 to n xi squares, right?
yes,
Mm,
sir.
plus or minus 2 times uh, so x1 2x1 mu 1 2x2 mu 2, like that. So it will become, what is it, it is x1 square minus 2x1 mu plus mu
It
square.
will become, sir,
So here it
minus
will be
2.
n mu square, right?
Yes, sir. It will become, sir, minus 2 summation of over xi's bracket bracket mu times,
Hmm. Hmm.
because we
Correct.
separate the
This
mu.
is right.
We can take common mu
uh,
from the sum. Yes, sir. It is correct.
so
Yes.
actually this is directly proportional to this part, right? And basically, can I say that like finally it will be e to the power minus half, I go to 1 to n xi square minus, what is it, n plus 1 mu square, right? Something like that. So this is kind of distribution you will get,
Okay, sir.
right? And what you do generally after that, you'll have to, you can actually try to see, right, how where it is, like how similar it to some other. You can find it like those solutions, I don't know, somewhere I find. mm, do I need to do this? Okay, maybe if you want, right, I'll just find out the solution, send it to you. maybe you can just post it on the discourse. I'll send you that part, but that is kind of normal distribution only, if I feel, and that will be your answer. So if I see that, and if your mean is 0, right, how much it will contribute here? It will not contribute much actually, right? So
Yes, sir.
that actually gives me that answer. But okay, if you need, I'll just share you the solution for it. You guys don't have the solutions for that, the practice assignment? You have,
No,
huh?
sir.
You don't have? Okay, okay, fine, fine. Maybe I'll ask them to upload it. And for this, if you need the like detailed one, right, I'll share that with you also. That's fine.
Okay, sir. Thank you, sir.
Yeah. Okay. That's it done then. Okay.
Yes, sir.
Yeah. Good night then. Bye.